Welcome to this session. In this session, we introduce the concept of trigonometric substitution. So this is majorly required whenever we want to find the values of integrals involving these radicals. Square root of a squared plus x squared, or square root of a squared minus x squared, or square root of x squared minus a squared. So when you see radicals of this form, then these are major cases or major problems where you need to do trigonometric substitutions. So let's give a few hints on this. So say this occurs when we replace the variable of integration by a trigonometric function. The most common substitutions are there are three. So the first one is called x is equals to a tan theta. The second one, we have x equals to a sine of theta. And third substitution is x equals to a sec theta. So these are the three trigonometric substitutions that we use. And you will know which case to use according to the structure of the integrand. So you say these substitutions are effective in transforming integrals involving square root of a squared plus x squared, square root of a squared minus x squared, and square root of x squared minus a squared into the integrals we can evaluate easily. So these are made from reference of right angled triangle, as we can see here. So the first case, when we say x is given by a tan theta, is the same thing as saying tan of theta is given by x divided by a, so just divide through by a. And you know from Oshachota, Oshachota is just an acronym to help us remember how to get the trigonometric ratios. That sine is opposite of hypotenuse, cosine is adjacent of hypotenuse, and tan is opposite of adjacent. So when you draw a right angled triangle, So this we call theta. So from Oshachota, tan is opposite. So opposite will be this side over adjacent. Adjacent is this side. And then from Pythagoras theorem, this side will be opposite of adjacent. So adjacent is small a. From my Pythagoras theorem, this hypotenuse will be the square root of x squared plus a squared. So x plus, so when I replace, when I say x is equals to a, so from this figure, we can say the square root of a squared plus x squared is the same as a times the absolute value of sec of theta. Now, with x equals to a tan theta, then it means that a squared plus x squared will be the same as a squared plus a squared tan squared theta, because you're squaring both sides. And then this is the same as a squared into 1 plus tan squared theta. And so this is the same as a squared, 1 plus tan squared is sec squared. So a squared sec squared theta. So which explains that if I get the square root of a squared plus x squared, then the same as the square root of a squared sec squared theta, which will give me a, and then what determines, because square root can be plus or minus, so that's why we are writing absolute value of sec theta. We can just write a sec theta. Then case 2, when we say x is equals to a sine theta, in the same language as saying sine theta is the same as x over a, and then we draw the right x over a, and then we draw a right angled triangle. So put here theta. So from Oshachota, sine is opposite of hypotenuse. So opposite over hypotenuse. So this side will be the square root of a squared minus x squared. So with this substitution, so with x equals to a sine theta, it follows that a squared minus x squared is equals to a squared minus the square of this one will be a squared sine squared theta. You factor out a squared, so it will be a squared into 1 minus sine squared theta. And by definition, sine 1 minus sine squared is cosine squared theta. So that's what we have. So then if you say square root of a squared minus x squared, then it will be a square root of a squared cosine of theta squared, which will be a cos theta, or to see that the square root has plus or minus sign, you write this one as A times absolute value of cosine of theta. And then case C, with x equals to A sec theta at the substitution, is the same language as saying sec theta is x over A. And don't forget that sec means 1 over cosine. So when you draw a right angle triangle, put here theta, sec theta is 1 over cosine of theta. Now from Oshachota, since we know that cosine is adjacent of hypotenuse, so sec, which is the reciprocal, will be hypotenuse of adjacent. So this will be x, and then adjacent is A, and this will be the square root of x squared minus A squared. So with x equals to A sec theta, then it implies that x squared minus A squared is given by A squared sec squared theta minus A squared, which you can write A squared into sec squared theta minus 1. But you see, definition of sec squared theta minus 1 is tan theta squared. So this will be A squared tan squared theta. So, which implies to get the square root of x squared minus A squared is the square root of A squared tan squared theta, which will be A tan theta, or A times absolute value of tan theta, if we have to respect the solution for square root, which can either be plus or minus. So let's quickly give the steps on how to apply trigonometric substitution. And the next session will give examples. So algorithm or steps for trigonometric substitution. Substitution. So there are 4 steps. Step 1, write down the substitution for x, and then calculate the differential dx, and specify the selected value of theta for substitution. So that is step 1. Once you have done that, step 2, you substitute the trigonometric expression and the calculated differential into the integrand, and then specify the result algebraically. So that's the second step. Step number 3, integrate the trigonometric integral, keeping in mind the restrictions of angle theta for the variable for the reversibility process. Simply for reversibility. And lastly, number 4, draw an appropriate reference triangle. Actually, it's a right angle triangle. Right angle triangle. To reverse the substitution in the integration result and convert it back to original value of x. So those are the steps we need to follow when we are doing a trigonometric substitution to evaluate a certain integral. And just to give those restrictions on expressions of those angles. So note x equals to a tan theta requires that theta to be the tan inverse of x over a with the angle between minus pi over 2 to pi over 2. So that's the range, or that's the domain of theta. That's the range or the margins of the interval of theta for it to be defined. And then B, substitution x equals to a sine theta requires theta to be the same as sine inverse of x over a with the angle between minus pi over 2. But this one we allow angle to be equal to the negative pi over 2 and also pi over 2. So that's the interval where angle is defined. And lastly, C, x equals to a sec theta requires theta to be the sec inverse of x over a with, now we have 0 less than or equals to theta less than or equals to strictly less than pi, because when angle is pi over strictly less than pi over 2, because when the angle is pi over 2, the value of sec theta will be undefined. So if x over a is strictly greater than or equals to 1, or pi over 2 less than theta less than or equals to pi, if x over a is less than or equals to minus -1. So that's the process, and the next session will be giving examples on how to apply those steps on specific problems. Thank you.